So hello everyone. I just want to remind everybody that your exam is coming up a week from tomorrow. And it covers quite a lot of material. Yeah, so I'll put up a sign up for the conflict, and you'll have the usual practice exam in your notebook, another one online, and another one in the Lawn Kappa. All right, so we have a lot to cover, so let's get going. So remember, we stopped at this summary, and just to review in chapter 20 summary of multiple regression, testing for the overall regression effect to see if there's anything at all in our model. All right, so here's just a good practice example. So we're on page 100. And let's just look at this practice example here. It says, okay, here's an example, and it's just a general model right here, multiple regression, and you're given the R, and you're given the sample size. And I'm just asking you to compute the chi-square and f-stats. To test the null, remember that all the slopes in the population are equal to 0, right? Against the alternative that not all, which is the same as saying at least one is not 0. All right, so what are we going to do? So how are you going to remember this? Because I know, now that I mentioned the final, I want you, the exam. Now that I mentioned the exam, I want you all to think about how, you're not going to have any formulas for the exam. So let's think about how to put this, how to remember this, how to remember all these statistics in a unified way. And so the first, what they all have in common is this r squared and 1 minus r squared. So here you're given r. So let's compute that first. So r squared is just going to be 0.1 squared here. So that's 0.01. And then 1 minus r squared is just going to be 0.99. Okay. So I think, let me just zoom in, and so this doesn't look very clear. Let me make sure it looks clearer for you guys. That looks a little bit better. Hold on a second. I rode my bike here, and my glasses are just so hard to see out of. And I don't have any, excuse me for a minute. Does anybody have a Kleenex? Just so I could use, sorry. So anyway, so this r squared right here, this r squared and 1 minus r squared. So okay, so I think the easiest one to compute is the chi-squared. And the chi-squared, remember the r squared measures the strength of the model. 1 minus r squared, oh thank you so much. 1 minus r squared measures the strength of the errors. So that's the core right there. And then for the chi-square, you just multiply that by your sample size. That's a super easy statistic. So that's the easiest one to remember. And then, so we can do that, and we get 0.01 over 0.99 times what? Times 100. So our chi-square statistic is 1.01. Okay? And I think if you remember this one, the other ones will follow pretty easily. Any questions on that? Okay, so now how many degrees of freedom for the chi-square 2? How many degrees of freedom does the chi-square have? Well, why is that relevant? In order to find the p-value, we have to find which chi-square curve to look on. So the degrees of freedom, if you can remember, is what? It doesn't depend on the sample size at all. It depends on how many parameters are in your model. So we've got 1, 2, 3, 4 parameters. So it's going to be what? P minus 1. The number of parameters, P is equal to 4. So it's the number of parameters minus 1. So it's going to be 4 minus 1, which is 3 degrees of freedom. So our chi-squared is equal to that. Okay? So we're going to look on the curve with 3 degrees of freedom and see what the p-value is. Now, do we know right away? Can you just look at this and know how many think? I don't want to do the eye clickers. I wrote a whole bunch of them, but I don't know if we have time to go back and forth. So I want to see how much we can cover because I want to get you ready for the exam. So how many people think this is significant? Just raise your hand. Remember what the chi-square centered around what? It's degrees of freedom. So we'd expect it to be 3. So do you think this could possibly be significant, anyone? No. You have to get way bigger than its degrees of freedom, much bigger. This p-value, if we wanted to look it up, it won't even be on the charts there. We'd have to go to the calculator, but this p, I looked it up and you can check, is approximately 80%. So what does that mean, that it's approximately 80%? It means that if there's nothing in our model, this r squared just agrees very much with the null, that nothing's going on. Because 80% of the time when the null is true, we'll get a p-value of 1.01 or bigger. So this model is just, there's no model here. R 0.1 is hardly any model at all. This would happen all the time by chance. All right, so now, let's say you just forgot how to do the f, right? You just forgot. So you remember this chi-squared, so let's just start off the same way. So now when you want to do the f, you'd say, okay, r squared times 1 minus r squared, and just repeat the chi-squared. Just do that much, and then say, oh, wait a minute. With f, don't I have to subtract something off here? Remember, you have to subtract off some little amount from n. Don't you always? What is that? What do you think it would be? P. So now you got most of it. So it's almost like this chi-square, but you have to subtract that little bit off. But then there's this other adjustment to make it centered at 1. This is centered at p minus 1. It's degrees of freedom. There's that other adjustment that Fisher, F stands for Fisher, made. And so we have to make that too. That's the p minus 1. So we just do those two things, and that's our f statistic. So this first part is exactly the same, right? 0.1 over 0.99. But now, instead of multiplying by 100, it's 100 minus p, and p is 4. There's 4 parameters. So you're going to have a 96. That would make them look very much the same. And in meaning, they are very much the same. You're going to get very similar p-values. This other adjustment down here, to divide by p minus 1, is just to make it really pretty, make it the mean of it 1. But it doesn't change the meaning of it, doesn't change the p-values you're getting or anything. It's just it's just normalizing it, basically, making it centered at 1. Okay, so that's p minus 1. So what is that? 3. So it's going to look about 3 times smaller than that. But its p-value is going to be very much the same. Okay? So there. That's what it looks like. Now, do you think its p-value? Remember, it's more conservative. It has a fatter tail, F. Fatter tail. Fat in the tail. Fat. P-value measures the tail. So do you think the p-value is going to be bigger than 80% or smaller? It has a fat tail. The p-value measures. So it's got to be bigger than that. The p-value is a measure of the tail. So it is, but not very much bigger. It's 80.87. Now, how would you look that up? You have 2 sets of degrees of freedom. So this is going to be an F, and remember what it is. The F has 2 sets of degrees of freedom. In this case, the numerator is going to be 3, and the denominator is 96. You're going to say the numerator is 3, but the 3 is in the denominator. What? Well, remember, this 3, if we filled out it, this 3 goes with our model. We just simplified it to look like this. Our model, R square, has how many parameters? 1, 2, 3, 4. We just subtract one of them off the intercept. It almost, okay? Because you don't have 4 degrees of freedom. Once you set, if you knew 3 of them, you'd know the intercept. Okay, so you have to have, so this is, you don't have 4 degrees of freedom, you only have 3. Okay? That goes with the model. And this one goes with the errors. Every single prediction you make, all n points, in this case all 100, has an error associated with it. But it's n minus the parameters. Okay? So that's how you should remember it. This next example is just, we'll do another time. It has you can do it at home. I just have to give you 2 more pieces of information. I said I'll give it to you in class, and you can work it on at home. We'll go over it another time. And it's a good one for practice for the exam. I'll give you r is equal to 0.5. That goes with this problem. And the standard deviation of the y's is equal to 10. Now you can do example 2 on your own. And we can do it, look at it again another time. Okay? Any questions? So let's turn the page. We're done with that. Now, what are we going to do? We are going to look at Z and T tests again. For what? Why are we looking at Z and T tests in multiple regression? Because for the individual slopes, we're going to do Z and T for the individual slopes. And everything's going to be the same as what we did before, except for one thing. And that'll just be, these slopes are based on, they're going to have a different degrees of freedom. We'll just have to adjust it slightly. Everything else will be the same. So let's look at this. Once we find out that at least one of the slopes in this is significant, which we did, not here, we didn't do that here. I'm going back to our last problem where we're looking at this, where was it? Sorry, this is what we're going to go back to, the one with the homework and the finals, and we got significance. Where is that? Here it is. Okay, so here, right here, we were looking at predicting finals from homeworks and exams. All right, so we're going to look at that again. Now we got huge significance for that, and now we want to know whether the homework slope or the exam slope is significant. So we find out that at least one of the slopes is significant. So now we can do Z or T tests on the individual slopes. Okay? So, and remember, these slopes aren't going to be the same as the ones in the simple regression. Okay. So, what do we need to think about? All right, so we can do Z and T tests for the individual slopes, right? The same way we do them for the simple regression, but we can't do it for the collective effect, okay? So when I say when I said in multiple regression you can't use a Z or a T test, that's for the whole collective effect to see if there's anything in your model, right? When you look at the whole overall regression effect, and you want to see if you're looking at all the slopes together, if they together contribute anything better than just the strict null, then you have to use a chi-squared or an F. But now once you find that's significant and we reject the null, when we reject the null, what does it tell us? That at least one of the slopes is significant, so we want to find out which one, maybe all of them. So that's what we're going to do now. Okay? So the F test told us that at least one slope, maybe both, in this model is significant. So let's test them. That's what we're going to do. All right? So let's just start with the homework one. All right? So the null is that in the population, that beta for homework, the beta slope, the slope is 0 in the population. And the alternative is that, that's a typo, the alternative is that beta 1 is not equal to 0 in the population. The reason we see a non-zero sample slope is because it reflects a real difference in the population, a real slope in the population. Okay, so the null means that once you control for exams, knowing someone's, remember the homework was significant in the simple one. We found it, but that doesn't necessarily mean it's going to be simple once you put it in the multiple, because once you control for exams, it might not be. So once you control, the null says that once you control for exams, knowing someone's homework score doesn't help you anymore predict their final. The small positive slope in our sample is just due to the luck of the draw. So it might not add any extra predictive value after we already have exams in the model. So it's super easy. This is what we always do. How do we do a z-test? We say the observed slope minus the expected slope, just that difference. The expected under the null, which is 0. This is 0, so we can just get rid of it. That's what our null says, it's 0. So this observed slope in our sample, which was that, we just say that over the standard error for the slope. We get that statistic, and then we just look at the sampling distribution of that statistic under the null and see how weird it would be to get it. All right? So it's too tedious to compute these standard errors with multiple x's, so we're just going to let the software do it for us. So this observed slope is just the slope in our sample. So it's just that right there. So we're going to calculate, this is what we're looking at, this slope. And we're looking at that standard error. Okay? So z is what? This observed slope, 0.1641, minus our expected under the null, which is 0, over its standard error. So this is really easy. And we get 2.27, so let's put that in there. And that's our z-stat. Okay? So we want to mark it on the curve here. This is a normal curve. We'll mark it on here. This is our z-score right here. And what's, okay, so that's 0. And we have -1, -2, -3. 1, 2, and 3. And right under it, I'm going to put the axis for the sampling distribution of our sample slope when the null is true. That's what we're saying. It's following a normal curve when the null is true. We're assuming that because of the central limit theorem. We have a big enough sample size. And so this is our slope, the sample slope. Now we'd expect it to be, our expected slope is 0. Right? That's what we expect it to be. But every time we take a sample of 100 and whatever n was, 107 students out of this larger, every time we take a sample of 107, we're going to get a slightly different slope. And how much it varies is given by our standard error for the slope. Okay? So we saw that so there's our slope of that tiny little slope. It looks like a tiny little slope, and you don't know where to put it on here until, you don't know where that falls until you translate it into a z-score. And now we know that it's right here. So it's quite unusual to get that tiny little slope of 0.1641. It's because the standard error is so small, because we have a big sample size. One standard error matches up to 0.07, right? So this is 2.27 of those standard errors. All right, so our z statistic is 2.27. Now, to find the p-value, we have to see whether it's a two-tailed or a one-tailed test, and that's given by our alternatives. Remember what the null is. The null is that in the population, beta 1 is 0, so we expect our sample to be 0, and then the alternative right there is two-sided. The alternative is that beta 1 is not equal to 0. We didn't say it was over here. That would have been a one-tail. We didn't say it was going to be greater. We just said that. So that means that we have a two-tailed test. So that means we have to take that tail. What our p-value is going to measure is the likelihood that we get as an extreme a value as we did in either direction. That's just because that's what we wrote as our alternative. So we're going to put it on the other side too. So here we have z equals negative 2.27. We're saying it could have fallen there too. So we have to take the area of both these tails. All right, so we marked z and we marked and p on the normal curve. Well, how are we going to get p? We'll have to look at 2.27. We have to, let's look at the table. 2.27, and that's between 97.56 and 97.86. Let's just approximate right here to 97.7% in the middle. Okay? So that means that together these two must be what? 100. So our p for the two-tailed test is going to be 100 minus 97.7%, which is equal to 2.3%. Okay? So together they're 2.3. So each one must be 1.15% on that side and 1.15% on that side. So if I asked you for if you had a direction here, like a greater than, the p-value would be half of that 2.3. It would be 1.15. Okay, and we conclude that we're going to reject the null. That's our usual 5%, that's less, and conclude that the homework slope is significant. In other words, we'd only, when the null is true, we'd only see a slope this extreme in either direction 2.3% of the time. All right, I think that's pretty much done here. Any questions on this? We don't have to worry about degrees of freedom. This is the basic idea. And it's just so simple. If we want to make things a little more precise, we can use a t, because we really didn't know the standard deviation of the whole population. So then we have to estimate it, and it follows a slightly different sampling distribution. It follows the sampling distribution of the slope. It follows a t-curve. It's just a little bit fatter in the tails, just a little bit. So that means that our p-value is going to be a little bit bigger. So why don't we do it? And okay, so now we're going to, it's the same thing. Here's our statistic. Okay, so the slope is, so let's just jump right to here before we even think about anything else. How is it different than the z? Well, we have the same observed slope. That does not change. That's our observed slope. We have the same expected slope of 0. Our null doesn't change, right? The only thing that we're making a slight adjustment for is the standard error plus. It's a little tiny bit bigger right there. So that means our t-statistic will be a little bit smaller, the statistic. That's all. So let's see if it is. It is a little bit smaller than 2.27. All right? So that's our t-statistic. But now there's another difference that makes it even, so that makes it a little bit smaller, but there's another difference that's going to affect things, and that is we have to look at a different curve than the z-curve, and that's where these degrees of freedom come in. So when we want to look at this same sampling distribution, we're looking at the sampling distribution of our slope, which is B1 for homework. That's the sampling distribution. It's slightly different if we take into account that we didn't know the standard deviation of the whole population. That's the big difference. So we'd still expect 0, still centered at 0. This is our t. It's just a tiny bit fatter in the tails. That's all. All right? But there's a different t-curve for each degree of freedom. So the degrees of freedom depend on your sample size. With bigger samples, this converges to a z distribution, to a normal distribution. So our degrees of freedom depend on our sample size. All right? So what are degrees of freedom? the degree, let's highlight it. The degrees of freedom are n minus the number of parameters in the model. It's the same as the degrees of freedom for the denominator in the f-test. It's not n minus 2 like it was in simple regression. It was only 2 because we had 2 parameters in simple regression. It's n minus p in general. Always n minus p. Even if you're estimating a mean, you basically have just one parameter, so it's n minus 1. Okay, it's always n minus the number of parameters. Now, how many parameters do we have? So now we have to think about it. We have 1, 2, and 3. So now we have to think about this. This is 3 parameters, and our n is 107. So those 2 facts are it. And so our degrees of freedom are n minus p, which is 107 minus 3. So we have to look at 104, that says 104. So we have to look at a t-curve with this is a t-curve. This is the t-curve with 104 degrees of freedom. And what do we want to find on here? I looked it up. I can show you. I did it by the online calculator. I looked up 2.24. First, let's just draw it. Okay, so we have 2.24. It's about there. Okay, and now that's where 0.1641 lives on the t-curve. And this is t equal to 2.24. Since it's two-sided, let's just do the same thing. So now we just have to find these. But before we even do, it's going to be a little bit fatter in the tails. So we knew before this was 1.15 and 1.15. Together they were, here, let's fill this in. We've got this information. This is 2.24. What I'm working on now is what this p-value is. And don't you know it's going to be, this is fatter in the tails. Don't you know it's going to be bigger than what we got before? We got 2.3 before. We got 1.15, 1.5. We're going to get something slightly bigger. Let's see what we get. Do you want to look or do you want me to just tell you? Raise your hand if you want to look. If you want to do it on the online calculator, raise your hand if you want. Want me to just tell you? Raise your hand. Okay, you want me to just tell you? Okay, I got that P in each one was equal to 1.36% here and 1.36% here. And together, I got a P of 2.72%, which is bigger. Does everybody understand that? Is the p-value using t-test always bigger? Yes. Because t has fatter tails. So you need more evidence to reject the null. All right, any questions on that? Now we can build confidence intervals the same way we did before. The only difference is this. The only difference is that you have to look at the degrees of freedom. The critical value for the t, the z is the same, but the critical value for the t is going to depend on its degrees of freedom because you have to look at that particular curve. So, confidence intervals for individual slopes using the t and the z. All right? So what do? These are 95% confidence intervals. All right? Should we just start with the z? With the z, we know that a 95% in the middle is going to be between 2 and -2, but approximately, but it's really more closer to -1.96 and 1.96. And that's the critical value, z star. Okay? So we can say this is z star. And there's where you see it, right here. And so if we wanted to build confidence intervals around the homework, what do? We take our homework slope. So a 95% confidence interval would be what? This is our point estimate, right? But we want to make a range. We say we're 95% confident that if we add and subtract 1.96 times the standard error, times that standard error, we'll capture the true population percentage. Basically what it says, we're 95% sure that this is the sampling distribution. This is Z, and this is our sampling distribution of the slope under the null. And we say, okay, when the null is true, 95% of the time we're going to get in this range. So 95% of the time we're going to get a sample in this range. So if we went 1.96 out in either direction, we'll capture the true population. You know, let's say it was here. 5% of the time we're going to be outside that range, and 5% of the time if we're here and we go 1.96 in either direction, we're going to come up short and not capture this true population percentage, which is right here. Okay? So that's the idea. And so now how will we do it? It's the same thing with the t. You just have to look up what the critical value for t is for 95%. And you can probably guess what? How are we going to think about this? Z, t's fatter in the tails. That means it's flatter inside here. So to get the same 95%, we're going to have to go out further. So these critical values will be bigger, just slightly bigger. You know, if you drew a t-curve here and you wanted to exaggerate, it's fatter, and it's 100%. It adds up to 100%. So it's fatter out here, it's flatter in the middle, which means you have to go out further for those critical values, just a little bit. So we looked at it. It wouldn't show up in a graph like this, but I looked up the critical value for 104 degrees of freedom. And what did I get? You can just do that on the online calculator. Does anybody want to see how to do that? You just put in 5% and look at two tails. And okay, so here it is. It's just T star. And it's going to be bigger than Z star. And T star is equal to not 1.96, but it's 1.9, not 6, but 1.983. So it's bigger. And this is negative 1.983. And that's the idea. And so that means these confidence intervals are going to be wider. See? This is the critical value right here. That's T star. So these confidence intervals are going to be wider. More uncertainty with the T. All right. So the question is now, do our confidence intervals agree with our significance test? What did our significance test do? It rejected the null. And our confidence intervals, you check, do they include 0? Do they? No. So that means we're outside this range. We reject the null. Is the same exact thing as getting a p-value of 5% in these tails, less than 5% in the tails. It's the same thing. It's logically equivalent. If one is true, the other is true. So see how this does not include 0? This does not. So that means that if we went in either direction, we're outside this range. The 90 inside there. So yes, it does agree. Why? Because our 95% confidence interval did not include 0. It's all positive. That's the same. That's logically equivalent to rejecting the null, rejecting the null, having a p-value less than 5% at alpha equals 5% for a two-tailed test, because there's going to be 5% total, right? rejecting the null, that the slope is equal to 0. For a two-sided test at alpha all right. Any questions on that? That says at alpha equals 0.05. That's the same as 5%. All right. Now, we're going to take a little glimpse into something that if you go on in statistics, you'll cover a whole lot, called model building, like deciding, okay, should we add another variable, and how do we know if it improves our model or not? And that is something that there's a lot of different software programs that do that, but I thought it would be useful for us to just do it by hand, just look at it a little bit, so that when you do see all these software programs, you'll know what's going on. All right, so let's do that. So adding a third variable to the model to see if it improves our fit. This is done a whole lot in applied stats courses at the 400 level, and you mostly let software do it for you. But I think it's huge, it's just really important to, at the simple level, see what you're doing and how it works. So that's what we're going to do now for the next, what do we have after that? Let's not spend too much longer. Let's just try to spend 10 minutes on it. Okay? So we're going to add a third variable to the model. So Z and T test showed that both homework and exam slopes were significant. Let's say they were both significant. We did it on the exams. It was even more significant. Right? So I'm wondering if I can even improve the fit by adding a third predictor variable. Would that significantly improve the prediction for the final? So I added labs. We used to give labs in Stat 100 as that's how they do it in a lot of classes. We had a lab, computer lab. So I added labs as a third variable. Now, how do you think that would change R squared? The key thing to remember about R squared is it's a measure of how close your predictions are to for your final. We're trying to predict their final exam score. It's a measure of how close our predictions are to their actual final. So, do you think if I add another variable, can I make a worse prediction? Is there any way in the world I can make a worse prediction by adding another variable? Do you think? The other variable is could be pos. Yeah, go ahead.
No, because if you add a variable that's not correlated, the R will stay the same.
Exactly. What he said is, no, it's not possible. Because if you add a variable that's positively or negatively correlated, it will give you more information and will improve your prediction, right? If it's correlated at all, it will improve it. It has to, because you got some more information. The worst thing is if you had something that was completely uncorrelated, just had nothing to do with finals, but then it wouldn't change anything. It would just keep your predictions the same. So your R squared, which is just completely just a measure of how correlated your predictions are to your actual values, has to either go up or stay the same when you add another variable. So that can't be the measure that we look at to see if, hey, it's a good idea to add this other variable. We have to look at something else. Okay, so here's an example of that. So let's look at this. So now we say adding a third variable right here. We say R squared has to go up or stay the same. And we can write that down. If the third variable, if x3 is correlated with y, either negatively or positively, it doesn't matter, that means we can improve our predictions. We have more information. So R squared will go up. If it's uncorrelated, with y, then we haven't lost anything, right? Then our predictions will be exactly the same. Okay, so here's an example. This is exactly what happened. All right, so I checked our, no matter what you do, we'll stay the same or go up. I checked R squared and saw it went up from, look how much it went up. This is so hard to see, gosh. You have your books in front of you so you can see. So here, what am I looking at? Here's without the labs and here's with the labs. And I said my R squared went up. So I'm looking at this. Look how little it went up by. Just a bit. Does that mean that adding labs is a help, significantly improves my model? Do you think so? Let's look at something else. Look, our errors went up too. That's bad. Our F went down. If we actually, we're going to get our p-values, you can't see it, it didn't show up, but our p-value would go up. So we have more error, we're going to have a bigger p-value, we have, it's, why is this working? Look what happened, let's just think about it. Does it significantly improve my model? No, our p-value did not improve. In fact, if you went out further digits, it got worse, it got bigger. So let's think about it. R squared went up. But do you notice that F, where's F? F went down. Why would that be? But F went down. Why? See, it went down a lot. So why? So let's zoom out a little bit here. Let's think about it. Okay, so here F was what? F is equal to R squared, 0.3841 over 1 minus R squared. So that's 0.6159. And then we have to multiply by the ratio of our degrees of freedom here, 104 over 2. And this is where we get 32.43. Look what happens over here. Now, R squared did go up, but did it really change things much? Look. It went up just a tiny bit. Sorry, that's not a 9.2, that's a 4.2. See? Went up just a, so we have 0.6158. But that's just about the same. That's not going to make this F go up much. But look what happens here. Now, our degrees of freedom, this doesn't change things much, but this really changed things. That's another reason why I like the F-stat. It shows you that every time you add a parameter to the model, look, see, that's the big difference. And I like the F-stat because it shows you that every time you add a parameter to model, it costs you a degree of freedom. So that means that you have to have R go up a whole lot to make up for it, or quite a bit, somewhat, to make up for it. So it's right in the model there that it's going to cost you a degree of freedom because it's easier. Every time you add a parameter, it's easier to fit a model. Even just random, you'll just fit random jitter in that particular sample. If you have as many parameters as you have data points, then you can always fit a perfect model, no matter what it is, right? So each time you add a parameter, it's going to cost you a degree of freedom. And that's what happened here. So it did not improve our fit. We'll get less significance. All right. So R squared did not improve enough to warrant adding the third variable, labs. Labs is not significant, as you can see. What do they mean? Where are we looking? Oh yeah, look, labs is not significant. Neither of these are significant. Now look at this. So these are not significant. See, we went from P equals 3 parameters to P equals 4. That's why it cost us this degree of freedom. Okay, labs, but this is a good question. But why did adding labs make homework change from being significant to being not significant. Okay, so interpreting these p-values in multiple regression are a little bit difficult. Could this be a mild case of what I've talked about before called the left foot, right foot syndrome? If you recall, I said, what if you have left foot? Your left foot size is an excellent predictor of your height. And so is your right foot. But if you put both of them in the model, they could both become insignificant. And you don't know, it's very confusing to interpret it because any linear, they're both measuring the same thing, and any linear combination of the two of them pretty much works the same way. So it's very difficult when two variables are highly correlated. It's difficult to interpret the slopes. So you always should check the correlation matrix to see if variables are strongly correlated. So I think probably maybe labs and homework are really correlated. So let's check. And sure enough, they are. That's a very high correlation between labs and homework. Yes. This means that both slopes can become insignificant when both are included in the model, even though individually they're both significant. Labs was very significant. We saw in homework, we were choosing between those two models before. This does not mean we should throw them both out of the model. All it means is that we can't do a good job of estimating how much of the prediction should be based on one or the other, because they're both predicting almost the same thing. Okay. Any questions about that? All right. So we should probably expand on this. Let's just go down here and just make sure you remember this, because it will come up a lot, that the question here says, does adding labs significantly improve the model even though your I-squared went up? So say no. Each time you add a parameter, R-squared has to either go up or stay the same. But it costs you a degree of freedom. So R-squared has to go up enough to make up for that. It costs you a degree of freedom. Let's go out a little bit so you can see what I'm writing. It costs you a degree of freedom. So you have to make sure that R-squared goes up enough to make it worth it, to improve your model. So F measures that, like when you look at the p-value for F. There's other ways you can look. There's something called an adjusted R-squared too, but right now let's just focus on, I don't want to overburden you with too much. All right, so that's pretty much the idea in the nutshell. And now, what do we want to do? So we have this conclusion. What should we do? I mean, if you really wanted to think about it now, okay, so now, what's the conclusion? We don't want to drop them both out of the model, right? Even though they both came up insignificant. So instead, what you want to do is you want to compare the R-squared, or you could do the F or chi-squared, for predicting finals from exams and homework. For comparing finals from exams, what are we doing? All right, so we want to do finals from exams and homework. That's this one. So we're going to have 3 parameters here. We're going to keep the parameters the same. And now we have the same number of parameters in the model. The only difference is this one has labs in it, and this one has homework. So side by side now, R-squared would make sense. because we have the same numbers of parameters, okay? So we're just going to see which model now gives a higher R squared, and that would be legitimate. So this is labs, and this is homework. All right, so let's look at it. So here we get this one, and here we get this one looks better. 0.3727 to 0.3841. Also look, we have less error here. That's going to go along with it here. Everything's going to be consistent here. This would have a smaller p-value if it went out to enough digits. The F statistic is bigger. All the measures go in the same direction here because we have the same number of, what I mean when I say they all go in the same, on any measure, this model's better because we're comparing apples to apples, the same number of parameters. All right, so which R squared is higher? Homework. Conclusion, the homework model is better. So when comparing models with the same number of parameters, then what? Then the higher the R squared means the higher the F, and it means the better the model. The lower the error, everything. Okay. You see, your error is related to your 1 minus R squared, right? That's what this question is. How is it related? So remember your standard deviation of the errors, you learned this back in Stat 100, the square root of 1 minus R squared times the standard deviation of the y's. So the bigger the R squared, the smaller your errors. And same for SD plus errors, which is just a slight adjustment because that's just equal to SD errors, the same thing, although, and it's going to be related as what? The ratio of n to n minus p, right? It's just a little bit bigger. All right, so now what should we do? We have two more things to do. And this next thing that we're going to do is one of my favorite things to do, and that is, just read the summary. This is a very good summary, but just read it on your own. And we're going to do a whole different way of doing a significance test, a non-parametric way, through computer simulations. Okay? And I like computer simulations because it makes you think about what you're doing when you're doing a significance test. You're testing that what you see, some difference you see, is just due to random chance. And it forces you to actually model that random chance. And then you can visually, it comes alive. You can see the sampling, an empirical sampling distribution of whatever your test statistic is, instead of a theoretical one that makes all these assumptions. Like we've been making these assumptions about how the errors are distributed and so forth, and so that we could use this idealized theoretical distributions, either the t or the z. They're both based on the normal curve, really. I mean, the z for sure, and the t is too. But it's based on the central limit theorem. But this is something very different. This is just an empirical histogram. We are going to model whatever we think is the random part. We're going to translate this situation into random draws, basically, or random assignment, and then look at the sampling distribution and look at our test statistic compared to what we would get under many, many randomizations. So this is called a randomization test or a re-randomization test. All right, so let's read about it and we'll do it. I think you'll like it. So the T, Z, F, and Chi-square tests all depend on the assumption, what? That the errors in our linear regression model are independent, identically distributed, normal zero sigma squared. The randomization test, also called the re-randomization test, has the advantage of not requiring normality. The randomization test is a completely new way of doing a significance test. It's a distribution-free way. Okay, so this is just what I told you, but I'll read it. Instead of computing a test statistic by estimating the standard errors, assuming theoretical underlying normal distributions, like the T and F does, that's what they really assume. That if you don't know, that's one of the assumptions to use them. Or large enough samples that the central limit theorem kicks in, like the normal and the chi-square test does. Instead, we use computer simulations to produce randomization distributions. And the coolest thing about it is this. It's not like one's better than the other. It's just like statistics is a bunch of tools. And none of them are going to fit exactly perfectly. Maybe like you want to compare them. How does one tool work next to the other one? So it's an opportunity for you to be able to do that. For you to say, if they give you wildly different answers, then that's really interesting. But usually they give you very similar ones. All right, so let's look. So we found this correlation between homework and finals in our samples of 107 student scores. This was, we did a while ago. We got this regression equation. And our null hypothesis is that the final scores are not related to the homework scores. That in the population, we see this correlation, but in the population, it's zero. We just happen to see this by the luck of the draw. Might be, you know, even when the correlation is exactly zero, you're going to get some R, non-zero R's, and this is small and just due to the luck of the draw. That's what it says. And the alternative is the same. The final scores are related to the homework. That we have a non-zero correlation or non-zero slope in the whole in the real population. So here's how it works. If there really is no relation between, here, let's just think about this for a moment. So what do we usually assume? We usually assume what? That, I tell you over and over again, that these 107 students were really drawn from a wider imaginary population or from a wider population of 2,000. Well, that's not true. That's not how, in this particular case, that's not how that happened. It is true in the homework you're going to be doing on confidence intervals. We have a giant class and you randomly sample from that. But generally speaking, it's not true. It's just not. So you're always assuming this. Well, there's something else you can assume. I don't know if it's easier or for you to imagine, but instead of imagining any wider population, you just look at the exact population of 107 students that you have, the exact population, and think about what it would mean if homework scores and final scores have no correlation to each other. What would that mean? Then it would mean that I could, if I just randomly paired up the homework and the final scores, just randomly did that, that would be, if there's no relation, then I'd be just as likely, the null would say that I'd be just as likely to get that, I could get that higher correlation. Do you see what I mean? Like I could take, if there's, like the null says, there's no correlation at all. So imagine, this is how we're going to visualize it, and tell me if you think this is helpful or if you can picture this. Imagine putting all the final scores inside a box, okay? And then randomly choosing one and assigning it to student one. So here's like, there were 107 students in the class. Here's the first 20. I'm just doing it the first 20. And these are their actual way they were paired up. So this student really got a 30.47 on the homework and really did get a 52 on the final. So these are the actual, right here. So these are the actual pairs, the actual X, Y pairs. But the null says that if there's no correlation, then So these are the actual pairs, and under this, when we did this, we got this correlation, right? We got this observed R right there. And then also says, that's just due to chance. You know, you could just randomly pair up these two and get that. You know, we could look at the sampling distribution of that, and that's probably not less than 5%. That's what the null says. Okay? So we could do that. Imagine putting all the final scores inside a box and then randomly choosing one and assigning it to the student 1. The next randomly chosen final would be assigned to student 2. Okay, and then we'd compute a correlation between the 107 homeworks and scrambled final scores. So pretend they're all in a box, and I shake them up, but I'll just like close my eyes and go like this, whoop, like that. Did I get one? Okay, 72 I got. So that's a random one, and I put right up here for the first one. I wouldn't put 72 back. I'd do it again. What did I get? 70. That would be the next person's score, etc. And I'd go all the way down like that. Now what would you have? Now you would have, these would be, if I pair these up, then what do I have? These are the random scrambled finals. So here I have the homeworks. They're homeworks. The homework, these pairs would be the homework and random finals. Okay? That's what I'd have. I'd have an XY pair that was just randomly assigned to each other. And so, so let's say we did that 1,000 times. We'd have 1,000 correlation coefficients, each computed from 107 homework and scrambled final pairs. And then we could make a histogram of the 1,000 R's. So it would be an empirical sampling distribution. So, so basically what we're doing is, this is a way to test what? So we're testing whether our observed sample R that we got equal to what? 0.3926? I should make a really little r here, because it could go either way. That is much different than the R's we'd get from random sampling. I can show you this on the computer, and then we can look at the book. Okay, so let's just go to the computer. And you can, so we'll just go to our data program. And we'll choose a data set. That's the grades. Okay, and so we have our scatter plot. We could have our scatter plot of, what is it, homework versus predicting finals. And there's our regression, and there's our R of 0.3926. Okay, we're saying how likely it's to get that just by chance. So there's another place we can go. We can go to regression here, and we can choose final and homework, and we get the same equation. We could do a chi-square, we could do an F and T, we could do a ANOVA table, we could do all our parametrics, whatever we want, but we can also do a re-randomization, and that's what I just talked about. So this is after 1,000 randomizations. So after doing randomly scrambling, after pairing them up, the homeworks and the finals, computing a correlation coefficient, and doing it 1,000 times, you're going to get 1,000 correlation coefficients. And that's your empirical sampling distribution, here it is, of R. And that is our observed R. and it has a p-value of 0 because we didn't get one after 1,000. But let's do more re-randomizations. Maybe we will get one, and that will change. Let's see. Watch, see if the 0 changes. Oh, yeah. Okay, so we got one. All right, so let's look at it. So there's the sampling distribution. It's looking more smooth. There it is. There's our sample, and we finally got one. And our p-value is 0. Or maybe more, 0.0%. It's an empirical distribution. I mean, it's going to change each time. So that is, it makes it come alive. All right? Now, let's go to the, does anyone have any questions about that? All right. So now let's just go back to the document camera. Now, unfortunately, so let's say we did that 1,000 times. We'd have 1,000 R's, each computed from 107 homework and scrambled final pairs. We could then make a histogram. So that would be the empirical or the experimental sampling. I have capital R here everywhere. Sampling distribution, I'll just leave it capital R because that's all our data program could do until this semester when I decided to change it to make it do little r. So the empirical sampling distribution of R under the null. So I didn't have it, these notes were published before, so that you're only seeing the half of the curve. You're only seeing the sampling distribution of big R. So if it was a negative, it just changed it to a positive. But we can still, it's the same idea. And so this is a histogram of it. And here's our observed sample R right there. And there's our p-value. And then we finally got something. There's our p-value. So that's the idea. Any questions on that? Any questions on that? I'm sorry I didn't, that's a new innovation. I like that you actually see the whole R, you know, for positive and negative, but we didn't have that available. So this is what it looks like here. Any questions? Okay. Now, we could do the same thing with multiple regression. We could do exactly the same thing. We could have our actual finals and your homework and exams, right? And scramble your finals to already existing homeworks and exams. And we could do that the same thing. So, you know, I could just go like this, and let's say I got a 56 there. You know, just anything. Let's say I got a 68 there. Let's say I did it again. I got a 76, etc. And I'd have a whole set of random ones, right? And so then you could, this is the actual homework and exams, and that other one is the random ones. So let me see if I can make this clear what's going on. So these right here are the actual homework and exam pairs. We're going to keep those together, right? And then what we're going to do is, of course, what we have, our observed R, is pairing them with your actual final here, right? So this is you have x1 and x2 and your actual y, and from that we got a sample correlation of 0.6198, and that's the correlation, the multiple correlation of how close our correlating our predicted finals with the actual ones, what we predict from our model with that, right? Now we could do the same thing we did here, and instead, each time, get x1, x2, and now you have random y's. And do that 1,000 times, each computed from 107 real homework and exam scores, predicting scrambled finals. So we'd be predicting, you'd get a correlation between your predicted based on your homework and exams, these actual ones, and this new scrambled ones. And then we could make a histogram of the 1,000 R's. And we did. And we get the same thing like this. This is what it looks like. So it would look like, so you can see you get this right there. That's, again, is our observed sample R. And now it's such a high correlation that I never got anything but 0. Okay? It's so far beyond the other, it's so extreme. You can see how extreme it is. So we'd have to do it a very, very, very long time before one appeared that far out. It's very extreme. And your P is 0. And I did it more and more times. This is after what? How many? After 100,000 randomizations. Sorry. After 100,000 randomizations, that's a typo. See, it's smooth. And I still didn't get anything, even close. Okay, so that's the idea. That's this R. That's our R equal to. That is it. Boy, I thought I was going to be able to cover more, like ANOVA, but we can't. So I'm going to have to extend the homework due date. It will have to be due Friday instead of Wednesday. You can do everything but the last problem.